There's a lot of other types of organic compounds that we're not really going to dive into at this level. One of them is being the class of cyclomolecules. Cyclo means circle, and I know a lot of you are going to struggle with the fact that it's not an actual circle, but because they're chained together instead of a straight chain into a circle, quote unquote circle, they're called cyclomolecules. So for example, cyclopropane. Prop means 3. So you have 3 carbons that instead of being chained in a straight line are chained in a grouping. So they would be chained like this. So even though the shape looks like a triangle, it's still considered a cyclomolecule. They're in a circle. Bute means 4. So you would have 4 carbons that are chained together, and I know it looks more like a square instead of a circle, but it's called cyclobutane. And then you have cyclopentane, so pent means 5, so you would have 5 carbons. Let me see here, 1, 2, 3, 4. So it would look like that. And so anytime you see that cyclo, that just means that they're all grouped together. And you can have side groups that are also cyclic. A big class of them come from benzene, and benzene you should know is C6H6. So you have 6 carbons, and then there's double bonds, like that. Now those double bonds are going to flip around, and they do it so quickly that we just draw a circle instead. So it has resonance. Those double bonds are flipping. That's resonance. And so we draw that circle for benzene. So if your IB question ever asks you or needs you to draw benzene, you would draw it like that, where it looks like a honeycomb. It's a branch of chemistry called aromatics. Here we have methylbenzene, so methyl, that's our side group. So instead of a hydrogen coming off of this carbon, it would have the CH3 group. You can make them a little bit more complicated. Here we have an ethyl and a methyl group coming off. Notice that we name it alphabetically, so ethyl, methyl, E, and then M. So benzene is very stable, and it's because of those resonance structures that makes it stable. It has sp2 hybridized, so you have overlapping of the p orbital, and you also have parallel orbitals forming that double bond. So there's 3 sigma bonds. It's 120 degrees, so it's trigonal planar in shape. That perpendicular bond that's creating that double bond is called the pi bond. The electrons are delocalized. It's very stable. It has low internal energy of the molecule. Because of benzene, it has a high degree of unsaturation. You have that double bond, and anytime you have double bonds, you're unsaturated. There's no possible isomers of benzene. It's reluctant to undergo addition reactions, but it will undergo substitution reactions, and we'll talk more about that in our next section, or 10.2. It's a toxic compound. A lot of you included that in your vocabulary, so it is a carcinogen. It can cause cancer. The bond lengths are between that of a single and a double bond. Sometimes you might see it written as a bond and a half because that double bond is there half of the time. But they're all equal, so there's no difference between them. There's a lot more information given in your textbook on page 480 if you would like more details. And then the last thing for section 10.1 are the trends in organic compounds. We've kind of already talked about this when we talked about our homologous series. The lower the member of the series, so the less carbons you have, they're likely to be gases or liquids at room temperature. The more carbons you have, the more liquid or even a solid possibly that you would be. More branches off the chain, you have weaker intermolecular forces, so you have lower boiling points. So again, the more branches you have off of the chain, the weaker the intermolecular force. And then make sure you take a look at Chapter 4, page 178 for the other properties discussed in terms of intermolecular forces, like melting points, boiling points, viscosity, those types of things. They're all there on page 178. And then here's an order of your organic compounds from the most volatile. All right, and remember, volatility is just how quickly it would go into the gas phase. And then the least volatile, so less likely it is to go into the gas phase. And that has to do with the type of intermolecular forces. So here they are listed for you. London dispersion is the more volatile, where hydrogen bonding, they're highly attracted to each other, would be least volatile. You're increasing the strength of the intermolecular attraction. You're also increasing the boiling point.